Warning: this stream is rated for mature audiences. Viewer discretion is advised.
All right. Good evening, ladies and gentlemen. Welcome back to the Legion Cage AdoptAPet.com theater. My name is Scotty, also known as EBC. And for the few people that are here at the moment, check out our current sponsor, which is not going to be our sponsor for much longer, Legion Cage. He requests you go check out AdoptAPet.com, where you can search for your local animal shelter and perhaps give an animal in need a forever home. So just go check out the website there, and all the information is right there. And yeah, we're going to be having a new sponsor here, I believe, in 1 week. We'll be switching over. I don't know if I'm even going to have a. I don't think I'm even having another stream on Twitch before that time, but we'll see. All right. So if you are not into the sciencey stuff, the math stuff, the electronics, all that stuff, this is probably going to bore you to hell. This is just me laying out and making sense of all the shit that my father taught me when we had our session together. And I was taking notes as quickly as I could. Hello, Watch Whitney. Which Whitney? Is this official now? Because I saw that. I'm just like, wait a second. Are we waiting until the week is up? Or are we making that switch now and we're just rolling with the homies? In any case, welcome. Hello. How you doing? I am also in Conflux Collaboration 1 if anybody would like to join me and yell in my ear. Trying not to. Okay, that's fine. I could, like time you out or something so you can't talk, I will hide that for a little bit longer. Hold on, I gotta do some things here with the things and the things. Where are we here? This thing and the other thing and that thing over there. Do. It's a priority. No, not that. Oh no, not that. Can't do that shit. Alright, there we go. That's what I want. Alright, now we can close that. Now let's bring up some musica. Let's see here. We got the musica. Let me turn that up a little bit. That's a bit much. There we go. Right about there. Okay. All right. So now, first of all, what my dad taught me was just some of the basics, and the primary thing I wanted to learn was how to solder, how to make good electrical connections with solder and a soldering iron, and he did that fairly well. We're not going to be pulling that out today. Probably when we get started on some junk electronics, we'll be doing stuff like that. So what I'm going to be doing today is just making sense to myself of everything that he gave me, and hopefully it's going to be something that you all can understand as well, if that's, something you're interested in. So hold on a second, let me bring this up. Let's make sure that's doing what it's supposed to be doing. It's not. So let's figure that out. Something like that. Okay, now I'm bringing this up because this is a kit that I bought on Amazon for not very much. That is like a broad sampling of the basic electronic components that are on every circuit board. So like everything on the right side, that's the technical term is circuit board, but cheese board, and there's a couple other terms that are used for that, and that's basically just what everything's attached to. Then there's all sorts of the parts and pieces, and they all have different ratings. That's what all the numbers are, is what that piece is rated for, how much electricity it can handle, how much it outputs, that sort of thing. So what I'm going to do first, how do I want to do this here? Let's see. I'm going to start with the metal film resistors. That I believe is these puppies here. No, those are the capacitors. And okay, so these are the LEDs. These are the what the hell are these? I don't know. These are the voltage regulators. These are the transistors. These are the adjustable resistors. Okay. These are the metal ones. Okay. So we're not going to use the cheese board. Then we've got LEDs there. Those are the ceramic capacitors. These are the aluminum electrolytic capacitors. These are the potentiometers. And let's see here. Those are the diodes. Yep, that's got to be it. Okay. So, let's get rid of this for a second. So this is the first thing. This is the metal film resistors. And you see they come stacked out like this. And see if you can see that number. That's how they're marked by the resistance that they have. They didn't do a really good job of marking this shit, but what are you gonna do? 33, okay. Now there's also, I know you can't see this on the camera, but there is a way to tell by the stripes on the resistors, and this was what my dad was trying to give me before. It's a color code, so that if you don't know based on like the way they mark these, you can find out based on the color of the bands on the resistor. So there's always 4 bands. And the first 2 bands are the actual numbers in the resistor. The third is a multiplier, and then the fourth is a tolerance level. And the fourth is always separated. And it's either gold or silver. Okay. So I can see that on these resistors. That's not a problem. Yeah, so at the very least, that's pretty easy to see the separation between the first, second, and third bands and the fourth band all by itself. There's a clear space between that. Like if you had 5 spaces, you got 3 on the left space and then 1 on the right. And what we're going to want to try to do is test these so that we have a baseline to know if it's actually doing what it's supposed to be doing and have that kind of a resistance. And for that, we need an electrical multimeter. So what this basically does is it sends a short electrical current, or rather a small electrical current, through the 2 things, and you got 2 probes here. So once you hook them up to something that is conductive, it completes the circuit, and then it tells me on the meter what it is rated for. So let me see if I can do this right according to what my dad taught me here. So we first want to turn on the meter for a resistor to so we want it on the ohm side, and we want to start as low as possible. So we're on the 200 rating. That's 200 ohms. And ohms is a measure of electrical resistance. So this is a resistor. So electricity is flowing through it, and it prevents a certain amount of energy from continuing on. It's like a valve almost. So you have, a certain amount of energy flowing through it, and it prevents it from allowing any more than a specific amount through, and that is its value, what it is supposed to be rated for resisting. So technically, let me see if I recall this correctly from what he said. We should be able to maybe get a reading on this. Let's see what we got here. It's also a little bit difficult, and my dad, who was an industrial electrician for many years, noted this. It's a little bit difficult sometimes to have things in a position where you can actually get it clearly. There's one thing that I'll probably get eventually that's an attachment to this. It's called gator clips. It's literally like a tiny little clip that attaches two wires. Okay, so we got it beeping, and it says 33, and that's what it's rated for, 33. And so we know that's good. If we test any other one in the series here, let's see here. Oh. Yep, perfect. 33. All right, so we know that the resistors that we're testing on there are good because it's beeping, which tells us that there is continuity. It beeps to tell us that it is a complete circuit. We're having electricity flow through the entire thing, and then giving us a rating of 33, which is what it's rated for. So now if I grab the next pack here, that's rated for 47, I think. No, this is 51. So we should get a beep and a rating of 51 on these. Okay, that's not coming up the right rating though, so maybe I'm reading that wrong. 33R. These are probably not in order. How much you want to fucking bet? Okay, we do have an order here, and it's probably not right. So this is a 10, and this is a 20, and then 33. Okay, so this is actually 1. Like, I was thinking there was a missing letter in the stamp there. No, that's 1. And this also goes weird jumpy numbers, like I'll show you this thing again. See how the numbers jump here? Starting in the upper left corner, it goes from 1 to 10 to 20 to 33 to 47 to 51 to 68, all the way down. And basically, all that is they have skipped so many. So they say, well, we want a resistor that rates 1 ohm. Then we want another one that's another level up. So we're going to jump all the way till 10. Then the next one is 20 and on. And there's so much space between those numbers because they want a little bit of leeway. So that there's a little bit of leeway on each side of that number, and they can and that's where the tolerance comes in. All right, so let's do that one more time. This is the 1. We're getting continuity, and it's coming up with about a 1.4, 1.5. That's acceptable. Yeah, about a 1.5. Let's test another one. That one's a little bit lower, 1.4. So that's acceptable, but it's so rare that you're going to use resistors that are that low on resistance, especially in something that's higher power. Okay, so that's a 1. Now let's pull out, this is the 10. See, now that was coming up 33. I think that just came off of the 33 one. Let's see here. Yeah, see, there's 10.4, 10.5, 10.2, 10.3. Okay, so that's 10. So that's why I want to be able to, what you just witnessed there, this was stuck on the end of this card, and if I examined it really close, I'll see the bands are different colors, but I tested it with the meter, and this one came up 33, so it doesn't actually belong on the 10 thing. It belonged on the 33 card, and it might have just gotten stuck or something when it was being put together. I don't know if I can put this with this one. Now that's one of the downfalls of getting something like this from Amazon and not paying a lot for it. They probably don't care so much about that, but that'll be with the other 33s. All right. So you get the general idea of that. Let me get rid of this. So what I want to make a note of is we test those. Okay. Now the second part to that is if, let me do something to attach this here. Give me a second. At some point in the future, I might have this better. I think I want to get a specific case to separate all of this into what it is. Okay, so now that's the first part. The second part, we got 1, 10, 20, 33, 47, and all the way up the line. Now, after we go through all those numbers, now we're in the 1000s, so say the next one is going to be a 1K, which is right here. Damn. Yeah, this thing is definitely going to have to come up with something different here. All right, so this is 1K. Now, it's not going to be able, I don't think it's going to be able to be measured on that lowest setting. Yeah, so I actually have to bump it up. And I think I should be able on the next setting, which is 2K, it should be reading up to 2K, right? Yeah. See, so this is a 1K and we're getting a reading of 1K. But the way this notation works on this meter is if that's a 2K and it says it's a 1.0, that means that stands for 1000. If it said 2, that sounds for 2000, and it keeps on doing that so that it can make use of the numbers as this goes up and up. So that's the 1K. I'm going to keep it in order like that. Then it goes all the way up through the tens and hundreds of thousands, and then the highest is this one, 1,000,000. So for that, I need to bump it all the way up to the 2 million switch. And let's see if we can get a good reading. Yeah, there we go. Let's let it stabilize right around 1.023 million. And all that means is that at that specific rating, it is designed to hold back 1,000,000 ohms. Worth of voltage. Yeah, that's a whole other thing that we got to get into later. All right, so that's that. And yes, I'm definitely going to have to find some container because the way they package this is kind of stupid. All right, so the next thing then is the diodes. Now, according to what my dad gave me, a diode is a unidirectional gate to eliminate alternating current or separate something from the rest of the circuit. Okay, so in order to test these, we're supposed to do the same thing in ohm rating. That's going to give us, if the diode is good, it's going to give us a reading according to the value in one direction, but the other direction is supposed to be 0 because it only allows it to go one way. So let's see what we got here. These ones, I think it's printed on the diode itself. So let's see, we've got... Oh, this I would have to look up, I think. 1N4007, 1N4148. There's only so many of them. So this is 1N58. I'm gonna need a magnifying glass too. $5819. Let me look that up real quick. See if I can get some information on what that's supposed to be. diode 1N5819. Yeah, that's all the science part I don't understand. So let me see if I can break this down a little bit easier. Okay, so this says man. Okay, so let me see if I can test this and see what the numbers are giving me. So this is the 5819. Let's drop that to like 2K. Okay, so I don't think I'm getting anything there. At least not properly. If I switch it then, no, I'm definitely not getting anything that way. Let's see here. Seems like it's holding a voltage for a quick minute and then releasing it. Put that on that. There we go. 0.177 on the one way, and on the other way, absolutely nothing. So that's doing what it's supposed to be doing. I don't know about the ratings on those yet, though, because they're not marked like the other things, like the ones we just did, the metal film resistors, by how much, with the ohm rating for what they resist. So the diodes have a different number that apparently is like a catalog number for the type of diode it is, and that resistance is built in. And they gave me only in this set 8 different kinds, as opposed to the resistors where I've got like, I don't know, 35 or 40. So at least I know that's one way I can test them and do what it's supposed to do. So if I'm pulling anything out of a circuit to test, I can simply look it up by the number that's on the diode itself and then determine whether or not it's doing what it's supposed to be doing. I'll have to do more research on that for sure. And maybe consult my dad again about that. he gave me some other little pieces of paper, like, you know, he was trying to draw diagrams and shit on little pieces of paper, and I took all that, and now I need to figure out what I did with all that too. That made better sense of some of this stuff than the notes I made on my phone. Alright, so at least we know what that is. See if I can get these back in here for now. There we go. So that'll definitely be next on the agenda, is getting a case to properly hold all of these things. Come on. Oh, wow. Okay. Now, the next part is the fun part, at least partly, that you would think, because you're probably very familiar with LEDs. And LEDs are a big part of circuit boards, and they're used in so many different capacities. And what LED stands for is light emitting diode. So it's that same thing that we just did, where it only allows electricity to flow in one way. So it could be like connected to a circuit in a specific manner that if it didn't do what it was doing properly, like it failed, then it might allow electricity to flow in the wrong direction or to a part of the circuit that it's not supposed to go. You only want it to go in one direction. So, same thing with this. It's only supposed to allow the electricity to flow in one direction, but it has the added benefit of lighting up. It's such a style. I don't know if you can see that. Let me turn this up a bit. Here, let me separate the leads. Yep. Turn off the light for a second. You look closely, there it goes. So my meter is running just a little bit of electrical current through the LED, and it's lighting it up. Now if I flip this around, we should have it do nothing, because it's only one direction. See, there we go. Alright. So LEDs are in circuits all over the fucking place. For everything, like the little tiny light that's on the side of whatever piece of electronic equipment you're using that tells you it's on or it's charged or whatever the case, that's an LED. And that's how they work. So we know that does what it's supposed to do. And they're all rated the same. The only thing that changes about them is the size. So like this, in this particular set, we got a 3mm diameter and a 5mm diameter, and they come in red, yellow, blue, white, green, which is all done by the dyed plastic casing that surrounds the light emitting diode. And you can do whatever you want with that. So this is definitely going to come in handy when I start doing some model starships, and we're going to do some lighting rigs on the inside of those models, and we'll build the circuit ourselves. We'll use some of the LEDs to actually produce the light that we want to come out, and either in a specific color, or we might be able to use the clear plastic with a color tint that's just like what's on these things. That's part of the set, so that when you shine a white light through it from the inside, it puts off a specific color light on the outside. So that's one of the fun things that I learned about electronics a long time ago, light emitting diodes. And they're fun to work with and all over the place. Okay, so that's that. Now next is ceramic capacitors. Now ceramic capacitors, a capacitor basically is taking a specific charge, essentially, and it stores it up and then releases it. So it stores up an amount of energy until it is at capacity and then releases it. And they're all rated different, just like the resistors. So for these, the ceramic ones are bidirectional, not polarity sensitive. They can go one way or the other. The tubular ones are polarity sensitive. Let's pull out that here for a second. Let me see what we got. Do I have any of those? Oh, that's that one. The aluminum electrolytic capacitors. That's these puppies here. So that's what we need to look for when we get to that next part, is these brown disc capacitors are supposed to go in both directions, and then these ones that are called aluminum electrolytic, they look like tiny little cylinders. Those are only supposed to go one way. So let's see if we can find the rating on one of these. This is 104. Okay. So this is a 104 ceramic capacitor. Let's see what we get on that. Now this is supposed to charge up a little bit, and then you reverse the polarity and it'll show a higher number than discharging. So we charge it up a little bit. And we flip it. And it's doing nothing. So I probably have the rating too low here. Let's bump it up to 20K. Let's try that again. Charge it up a bit. And flip it. Still nothing. Okay, let's bump it up one more time. Charge it up. And flip it. Nada. Oh, this might be the one I have to, might have to flip over to volts here. Let me... Yeah, because we're not testing resistance anymore, right? So let's try it on this first. On what do we got here? It's 200 milliamps. No, 200 millivolts. Okay, charging it up. Flip it. Oh, come on. You're killing me. Nothing. Let's try it this way. Okay, let's try doing that. We'll try one more time here. Nada. Okay. All right, let's do this one more way here. See, that's AC, and I think that's DC. Let's switch this over to amps. Nada. And one more time, we'll bump it up to 1,000 amps. Nothing. All right, so clearly I don't understand that. I'll have to get with my dad again and see what he says. Because I probably wrote it on those little tiny pieces of paper, but I don't know how to check that. You know what, let me do one more thing here. While I'm thinking about it, because I do have a note in here that says, yeah, maybe I was doing that wrong. Okay, so this is a 104. Now, if we put it on, let's start it on 200 ohms and then switch it over to volts. Yeah, because now I see a note in here, checking with ohms, charges should show nothing, then on volts, it's going to discharge what was built up. So let's try that. Okay, so we charge it up. Then we switch to volts. That definitely showed something there. Negative. Yep, there we go. Now it's all discharging. Okay, I think we got it now. So let's go back 200 here. Charging it up with the ohm half of the tester. And we're flipping it over to the volts half of the tester, and it's reading the voltage that was on it. Okay. Yep, there it was, and now it's dissipating, and that's right. Now, what I don't know about this is the ratings on these. Obviously, it's something to do with just how much energy it can hold before it discharges. But I don't have quite as clear an understanding of how the ratings on these are. And there's 25 of those. Alright. Get all this mess back in there. If I do have, I might need a couple of different cases for this. If I want to separate them out according to all these readings. Okay. Now I'm not going to test these, but like I said, these ones are the brown ceramic ones that look like a little disc, are supposed to be bi-directional. You can put them into the circuit any which way, and it doesn't matter. These ones that are, they kind of look like a black cylinder, they only go one way, so you have to wire them into the circuit a specific way, and they're actually marked on there, one of the two leads coming off, which one of those has to be in the specific place. And I have to look into that too. So let's make a couple of notes on that here. Here, let me flip this over so you can see what I'm doing. So the note I need under the ceramic capacitors is how to measure the rating and how to measure the bidirectional quality. Then under the aluminum electrolytic capacitors, which side is which? Arrow points to which side for unidirectional discharge. Okay. All right, so that's it for the capacitors. We'll put those away for now. Then we have that's the capacitors, the LEDs, the electrolytic capacitors, which are the unidirectional ones. Now we've got the potentiometers. Okay, so adjustable potentiometers, and these ones are marked with a 3-digit number, 101, 201, 501, 102. And they do a weird succession on these. So we do 100 ohms is 101. 200 ohms is 201. 500 ohms, 501. Then 1,000 ohms, 102. And it's like, wait, okay, that doesn't make sense. But apparently this is just, stuff that's been set in stone for years and years on how these things are marked. All right, let me check on something real quick. All right, so potentiometers. Let me get this thing here. Do I even have a note on this? I don't think we got to this. Yeah, I don't think we got this far, so let's just play around and see if we can get some kind of reading on this. Adjustable potentiometers, I think. No. 3296. Ah, yes. There we go. So if I recall correctly what my dad was telling me, a potentiometer is another type of thing to kind of clean the electrical current and smooth out the waveform of the electrical current. And adjustable potentiometers, once you have them in circuit, I don't know if you can see this. Let's see if we can get a close-up. You can see a little tiny screw on the top of it. You can see the brass, I'm sure. I don't know if you can see the slot in there. And you're supposed to be able to turn that screw head to adjust it to whatever you need. So I'm seeing the numbers here. So here's a 102, 103, here's a 202, a 104, here's a 504. So let's see. Yeah, let's just pick this one. So this is a 504, which is 500,000 ohms. So if I put this on 2 million ohms, no, 200,000. Yeah, if this is rated for 500,000, then we want it on 200,000 on the meter. I think that's right. So let's see if we can get a reading off of this like that. Nothing there. We definitely got something there, I think. Like I'm getting a little bit of a reading and then it goes away. Let me bump this down a bit. nothing. Let's bump it up 1. 2 million. There we go. Okay, so if this is supposed to be 500,000 ohms, and it's coming out at 488, at least on that, and it has 3 leads, which, if I recall correctly, what my dad was telling me, that one of them is a ground, but I'm not positive on that. So let me, if I do it on those 2, I get a 233. If I do it on that, I get a 488. If I do it on that, I get a 233. Okay, now I recall what he was telling me. Something about, like, because you got half on one side. Let's look this up here. Just so and let's get let's add a new window capture. Yeah, there we go. Okay, so a potentiometer is a manually adjustable, variable resistor with 3 terminals. 2 terminals are connected to the ends of a resistive element, and the 3rd terminal is connected to an adjustable wiper. The position of the wiper sets the resistive divider ratio. Okay, so you can actually change which side of the potentiometer gets so much resistance. I'm not exactly sure why that would be something you want to use as opposed to just 2 resistors, but yeah. Let's watch a video. Give me a second here. There was another video that I wanted to watch a little bit later in this, so
Advertising on YouTube helps me reach engaged customers like Jenna, who's been searching for landscapers.
In this video, we're going to talk about potentiometers. Potentiometers are devices that can limit the current flowing in a circuit. They can attenuate a signal or even reduce the voltage across certain elements. Potentiometers are essentially variable resistors. This particular potentiometer has 3 terminals. We'll call the first one A, the middle one B, and the last one C. As you rotate it towards the right, that is in the counterclockwise direction, the resistance between points B and C increases,
okay.
whereas the resistance between A and B decreases.
Yeah, that makes sense.
And if you turn it in this direction towards A, that is in the clockwise direction, the resistance between A and B increases, while the resistance between B and C decreases.
Got it.
And we're going to talk about the math regarding this shortly. So here we have the electrical symbol of a potentiometer or a variable resistor. This is point A, point B, and point C. Now let's say we have a 50 kilo ohm potentiometer. What you need to know is that the resistance between points A and C is the value of the potentiometer. It's 50
okay,
kilo
so
ohms.
it's 50 total
Also,
across the whole thing.
between points A and points A and C rather, is the sum of the resistance between points A and B and the resistance between point B and C.
Right, so you're basically dividing it in half between 2 sections, and They both
then the
have to add
resistance
up to
between
the
B and
total
C
amount that it
is
can
going to be
take.
40 kilo ohms.
10 plus 40 equals
If you
50.
turn the
Okay.
dial halfway, then AB will be at 25, BC will be at 25.
Okay.
If AB is 30, BC is 20.
Yep.
So these two must add up to the total resistance. Now let's draw a picture of the potentiometer so you can get a better visual illustration of this. My drawing's not perfect, but we're going to make this work.
It's a drunk horseshoe.
So this is going to be point A, B, and C.
All right.
Now let's say that this particular potentiometer has a resistance of 100 kilo ohms. If we set the dial right in the middle, the resistance between A and B will be 50, and the resistance between B and C will be 50.
Yep. Perfect.
The resistance between A and C will always be 100 for that particular potentiometer. Now what happens if we set the dial at the quarter mark? That is 25% of the full swing.
You get 25 between A and B,
mark,
and then 75 between B and C.
The resistance of A and B is going to be about 25% of 100 kilo ohms, which is 25K. And that means B and C has to be 75K.
Yep.
Likewise, if we turn it to, let's say, the 40% mark, the resistance between A and B will be 40K, while the resistance between B and C will be 60K. So that's just a visual illustration of how this potentiometer works and how you get the corresponding resistance values based on which terminals you're using. So you can use all three terminals in a circuit or even just two. For instance, if you just use A and B, you can use it as a current limiting resistor, a variable current limiting resistor. So let's talk about the different ways in which we could use a potentiometer in a circuit. So one way in which we could use it is in the voltage divider circuit. So this is our output voltage. Now let's say the input voltage is 12 volts. We're going to use a 12-volt battery. So this is going to be point C, point A, and point B is attached to the output. So the output voltage is going to be the input voltage, which is 12, times the resistance between points A and B divided by the total resistance between points A and B and C, which is basically the
Lucidchart makes intelligent diagramming easy and helps your best ideas become real.
resistance between A and C. So the resistance between A and C is fixed. If we use the last potentiometer, that's going to be 100 kilo ohms. What's not fixed is the position of B along A and C. So that can vary. So thus, this potentiometer can control the output voltage. So the output voltage could swing from 0 to 12 volts.
Right.
If you swing the knob towards point A, you're going to bring the voltage to 0 volts. If you swing it towards point C, you can bring the voltage to 12 volts. If you put it in the middle, you'll get 6 volts. If you put it at the 25% mark from A to the middle,
you get 3 volts.
You'll get a quarter of 12 volts or 3 volts. At the 75% mark, you'll get 9 volts.
Okay, so basically what he's saying, if you attach a 12-volt battery and your circuit only requires some of that power, so you don't want all of the power from the 12-volt battery entering the circuit, you would adjust your potentiometer to whatever percentage you want to enter the circuit. So if you adjust the potentiometer to 25%, you're going to get only 3 volts out of the battery actually entering the circuit. So that makes sense. Now, I'd have to spend some more time on the math aspect of that because he started writing out these equations, which for what he's writing there is actually basic electronic equations, but it started fuzzing my brain up there, and I'm usually pretty damn good at the math. But then he started explaining, okay, this is how that happens, and then it started clicking in place. So if I were to do something like that, I mean, eventually I'm going to be building my own circuit for these kinds of things, and I'm going to be using 12-volt batteries, or maybe, depending on the size, if I'm doing a lighting rig for a model Starship, maybe a double A battery or a triple A battery. Although I got to imagine that uh, based on whatever we're looking to do, I think a 12-volt battery is probably going to be best, but I don't know for sure. It just seems to me that I think I've read somewhere that when you're doing stuff like that, 12-volt batteries are better. But that's definitely going to be a big part of it if we're designing our own circuit, deciding, what we're going to need to do all of that from scratch. I do know you can buy lighting rigs that are already made, and or at least the individual components. But I think aside from like individual spooling wire, hookup wire they call it, where you're actually hooking up components between various things and creating the circuit. I've got all of the components I need here, as far as I know. So, all right, so that gives us a basic understanding of what a potentiometer does. And when I was testing this other one, that makes sense because the one I was testing here was rated for 500,000 ohms, and I was getting, when I connected between A and C, I was getting 500. When I was connecting between A and B, I was getting 250 almost. And when I was connecting between B and C, I was getting 250. So that checks out, which tells me that the potentiometers that are brand new here are also set halfway in the middle. So if I was to connect up a 12-volt battery to this potentiometer that's rated for 500,000 and use it exactly as it's set right now, it's going to give me 6 volts. At least according to that portion of it. Now, let me continue playing the video here just so we can see if there's any more to that.
And so by turning the knob, you can vary the output voltage from 0 to the maximum of the input voltage. So that's how you could use a potentiometer in a voltage divider circuit. Now, there's some other ways in which you can use it as well. So let's say you have an AC signal, or a signal carrying a sound wave, and you want to adjust the volume across the speaker.
Okay.
So what you need to do is connect the potentiometer to a speaker like this. So the input signal, you want to connect it to points A and C of the potentiometer. The speaker at the output, you want to connect it between points A and B. And so let's say the signal varies from, let's say it has a peak voltage of 10 volts. Now, the output voltage will vary from 0 to 10 volts, and you could adjust it. If you swing it towards A, it's going to be at 0 volts. It's going to be off. If you swing it towards point C, it's going to be at its maximum volume. So in this particular way, you could use a potentiometer to control the volume of the sound at the speaker. So that's another way.
Holy shit. Okay, so that basically means that anytime you have a volume control knob, you are actually turning a potentiometer that allows so much voltage from the circuit into the line that goes to and from the speaker, and that actually turns up the volume as you crank it up and allow more voltage in. See, now that's amazing to me. That's truly amazing that you can see something like that in a basic circuit that looks complicated and hard to understand, and see that real world application right there. Wow. Okay. Well, that also clears up a lot of other things too. I mean, I've got several potentiometers here that came with this set. If I need something to do with this circuit, like again, going back to me using a lighting rig for a Starship model, let's say I want the lights to dim, I could use a potentiometer to make it go from only a little bit of voltage going through the circuit and causing the LED to light up, to more voltage going through and causing it to light up brighter. So you could actually install a dimmer function on the lighting rig for the model. That's interesting. Okay. All right, let's see what else we got
way
here.
in which you can use this device. So in this manner, what we're doing is we're decreasing the voltage across the speaker. And so this is a form of signal attenuation. But sometimes we may not want to decrease the voltage. Instead, we may want to limit the amount of current that is flowing in an element. In this case, we could use a potentiometer for brightness control. So let's say we have a battery and we have a light bulb. And we want to control the brightness of the light bulb. The brightness of the light bulb is directly proportional to the current flowing through it. And so by increasing the resistance, we can decrease the current flowing through a light bulb, thus decreasing the brightness. If we want to decrease the resistance, we'll increase the current and thus increase the brightness of the light bulb.
Yeah.
So we can adjust the brightness.
That's
using
exactly what I was just talking about.
Now, this circuit is going to be different than the previous two circuits because we don't need to use all 3 points of the potentiometer. We can just use 2 out of the 3 terminals. And that's what we're about to do here.
Okay, so he's using A and B, but not C.
So this is terminal A, B, and C. In this circuit, terminal C is not used. Or rather, let me say that again. It's not being used.
Okay.
Let's say we have a 6-volt battery.
Okay.
As we turn the knob, we can increase or decrease the resistance between points A and B, depending on the direction in which we're turning. So if we decrease the resistance, there's going to be more current flowing in the circuit, and the brightness will increase.
Yeah, okay.
That is, if we turn the knob towards A, that's going to be the clockwise direction. Actually, I take that back. If we turn the knob towards A, based on the picture that I had in the beginning of the video, RAB goes up. It increases if we turn it in the clockwise direction. So the current will decrease, and thus the light bulb will become dimmer. Now, if we turn it towards C, the resistance across A and B will decrease. And this is in the counterclockwise direction.
Okay.
And if we decrease the resistance between points A and B, the current flowing in the circuit increases.
And the light
and
gets
so
brighter.
the light bulb becomes brighter.
Amazing.
And so that's the basic idea behind how the potentiometer works. You can use it to adjust the output voltage across a circuit. You could use it to control the volume of sound in a speaker, or you could use it to adjust the brightness of a light bulb. There are other ways in which you could use it as well. You could use it for oscillators to control the frequency of a circuit by adjusting resistance. So anything that is affected by a resistor, you can modify that effect through a potentiometer. So that's it for this video. Those are some of the applications of potentiometers. Thanks for watching.
By advertising on YouTube.
Cool stuff. Interesting. All right. Well, having tested that, then I'm pretty sure that it's working the way it should be, because I was testing that and it was giving me exactly what that just described. So essentially, if we're looking at one of these, so like that's the one I was testing, we got A, B, and C. If you turn it clockwise, it gives more of the value to A and B. Whatever you have A and B connected to. If you turn it counterclockwise, it gives more of a higher percentage of its value to B and C, whatever that's connected to. So it's kind of like a bidirectional gate, or like a faucet that's got two valves on it, and you're controlling. Oh, you know what would be a perfect way to describe that? A standard sink faucet, or kitchen or bathroom faucet that's only got one knob on it, and you either move it to the left to allow more hot water, or to the right to allow more cold water. Interesting. Well, that's very cool. I didn't even think about that real world practical application, like allowing using a potentiometer to control the volume of music, or controlling the brightness of a light. So that's very cool. All right, let me see where we were here. I don't think I need anything more on that. I mean, aside from understanding that if I'm building a circuit, that I'm going to have to determine which potentiometer is going to do that. But I could also build the circuit without the potentiometer first, to ensure that the circuit is doing what it's supposed to be doing, delivering the voltage from the battery to the LED or set of LEDs and lighting them up properly. Then I could maybe put in a potentiometer to see if I could create a dimmer circuit out of that. Interesting. Okay. All right, well, that's enough for that then. Then we have transistors. That's these puppies. I think. No. Yeah? I think those are the transistors. Let me go look at the picture. Yes, those are the transistors. They look like a little black piece. Here, let me turn that back up. A little black piece. This section in the top right, next to the left of the PCR boards. So it's got a little black cylinder that looks like it's cut in half, and 3 wires coming out of it. We didn't get to this either, so why don't we do the same thing and see if we can watch a video on transistors. Hold on. That's a organic chemistry teacher. Let's see here. Let's just search transistor. How long is that? That's 18 minutes. Let's do this one here.
If you shop on Amazon, you
I
should use
don't
this
shop
tool.
on
It's a
Amazon, so I'm
browser
not going to use
extension
that
that
tool.
automatically compares Amazon to
Blah,
other
blah, blah,
sellers.
blah, blah. Buy our shit.
Almost a century ago, computers were built with large vacuum tubes and were very big.
Yes.
And by big, I mean huge. Some computers, in fact, were large enough to occupy an entire room. Fast forward to 2018, and computers are smaller than a matchbox and can be strapped to our wrists. This incredible evolution was made possible by the invention of a device no larger than a hair clip, the transistor. The transistor is probably the greatest invention of the last century, or perhaps one of the greatest of all time. A transistor is just three semiconductors glued to one another. A semiconductor, as the name suggests, is a material that conducts, but only partly. The conductivity of a semiconductor, like silicon or germanium, lies between the conductivity of a metal, like copper, and an insulator, like rubber.
Okay.
A semiconductor normally conducts at high temperature, but we can also make it conduct by injecting it with impurities. This is called doping, and is done, just like when it's done in sports, to improve performance. A semiconductor is either doped with an atom that carries an extra electron, or with an atom that is deprived of an electron. The vacancies left by migrated electrons are called holes, and are considered to be positive charges. The former then becomes an N-type semiconductor, while the latter becomes a P-type semiconductor. It is critical to remember that the resulting semiconductors are not charged. They are, in fact, electrically neutral. The donors, having donated electrons to the N-type semiconductor, are now positive. Similarly, the acceptors have accepted electrons from the P-type semiconductor are now negative. Therefore, the semiconductors contain the same number of charges. However, they are named so because of the type of charge that is free to move and carry the current in them. When a P-type and an N-type semiconductor are sandwiched together, what is formed is a diode. However, when an N-type semiconductor is sandwiched between two P-type semiconductors, or vice versa, a transistor is formed. A diode is a pipe through which a constant current of water can flow in only a single direction. A transistor, however, is like a valve. It allows us to control the current flowing through this pipe by rotating it. In one of the most commonly used transistors, the source of water is formed by a highly doped N-type semiconductor called the source, and the end of the pipe is formed by a lightly doped N-type semiconductor called the drain. The valve is formed by a moderately doped P-type semiconductor that is sandwiched between them. This is called the gate. Now, because the semiconductors are electrically neutral, no current flows through them. We need to create an excuse for their charges to move and therefore constitute a current. When we apply a positive voltage to the gate, the electrons of the highly doped source are lured towards it, and the holes of the gate are repelled away from it. This gradually opens a channel from the source to the drain, which the electrons cross, thereby constituting a current. Applying a voltage to the gate is analogous to rotating the valve to remove the barrier that prevents the water from flowing from the source and out from the pipe. By varying the degree of its rotation, we can control the amount of water that flows in the pipe. This is the working principle of a transistor. Now, we can design the valve to allow the water to flow through it only when it's rotated to a certain degree. When rotated less than this threshold, it stifles the water flowing through the pipe. In this way, a transistor acts as a switch. This is how binary numbers are generated. Each bit, 1 or 0, is either an open valve whose magnitude of current is standardized as 1, or a closed valve, which translates to 0.
Okay, that makes sense.
The sequence of bits is then manipulated by microprocessors to implement a myriad of operations. These switches are extremely fast, but most importantly, extremely tiny. The computer on which you are watching this right now is powered by a bed of silicon covered with billions of transistors thinner than a strand of hair. The ridiculous scalability of transistors is dictated by Moore's law, according to which the number of transistors
this is
populating a
getting way too
microprocessor must
complicated for
double
me.
every year. Naturally, an increase in transistors causes an increase in processing speed. Intel's best chip in 1985 employed less than 250,000 transistors, compared to the almost 3 billion transistors that Intel's best chip now employs. The increase in speed? Intel's best chip in 1985 would take 4.5 hours to process what Intel's best chip now can process in a second. That's speed. If it weren't for this scalability, we couldn't have developed billions of smaller, faster, and cheaper devices, including computers, telephones, GPS devices, flashlights, radios, gaming consoles, televisions, routers, and a device no larger than a human hand that integrates all these indispensable technological.
Okay, so obviously this is trying to explain a difficult concept to somebody that doesn't have any understanding of it, but that was very difficult for me to understand, the whole explanation about how it works. So if I gathered that properly, a transistor is 3 semiconductors sandwiched together of varying positive or negative charges, but that's not quite right. It was something along the lines of that because of the way it is designed, it induces electricity to flow in one direction or the other based off of the way the material that makes up the semiconductor is charged. And that was what he was talking about, in injecting or doping the material with a positive or a negative charge. So I'm not sure I really understand that, but I think I got the basic concept that it is a type of a gate, a type of a valve, in which the primary purpose seems to be that you either want it open or closed, and that is what gives us the basic concept of zeros and ones. Okay, so I think I understand that. I'm not sure where that would ever come into play for any type of circuits that I'm making, but I don't know for sure. So I think I'll definitely at some point have to do some more research on that to get a better understanding of what a transistor does. Maybe I just need to watch other videos that are explaining a little better here. All right, what do we got next? We've got here, let me get rid of this. Okay, so next is the adjustable resistors. That's these little puppies here. It seems to have the same function as a basic resistor, but it's got a little switch in there so that you can adjust what its value is. That seems to be taking it a little bit more complicated, like something that you want to adjust in the middle of a circuit, I'm assuming. So I don't know that I will ever use that either. And then the final thing is a voltage regulator. And this was specifically designed to smooth out the waveform of the voltage that is coming in. So give me 1 second here. There was one more video that I saw, I want to say a couple of months or weeks ago, that explained one of these concepts much better. Let me see if I still have it saved here. Here it is. Let's see. Let me do this. Copy link. And then let me put this over here. Okay, so I got one more video here I want to watch again, and let's take this. Step by step and see if we can understand this.
When advertising on YouTube, I know that making an authentic video with a clear call to action is the key to getting
This video was sponsored by Caseta by Lutron.
Imagine you have a giant circuit consisting of a battery, a switch, a light bulb, and 2 wires which are each 300,000 kilometers long. That is the distance light travels in 1 second. So they would reach out halfway to the moon and then come back to be connected to the light bulb, which is 1 meter away. Now the question is, after I close this switch, how long would it take for the bulb to light up? Is it half a second, 1 second, 2 seconds, 1/c seconds, or none of the above? Now you have to make some simplifying assumptions about this circuit, like the wires have to have no resistance, otherwise this wouldn't work, and the light bulb has to turn on immediately when current passes through it. But I want you to commit to an answer and put it down in the comments so you can't say, oh yeah, I knew that was the answer when I tell you the answer later on.
This question actually relates to how electrical energy gets
let
from
me-
a power
let
plant
me,
to your home.
Let me pause that there, because when I was first watching this video before, I didn't understand what he was talking about there. Or rather, even if I had a rudimentary understanding of what he was asking, I sure as hell didn't know the answer. He was basically saying the amount of time that it takes for light to travel. Okay. Is electricity the same type of thing? How long would it take if you stretched it all out and you had no other factors doing that, for the electricity to completely go around the circuit and light the light bulb? And I didn't understand that whole thing that he was talking about in the first place, because, well, more than likely I just, it just didn't click. And it still really doesn't click what he's talking about. And this channel, Veritasium, this guy covers so many very complicated subjects that you have to have a much better understanding of mathematics and chemistry and electronics and everything else just to sometimes get what the hell he's talking about. So I clearly didn't have a full understanding of what he meant there, but I had a basic understanding, I think. So as we go on to the rest of this video, it becomes more clear what it is that he's trying to demonstrate and why that is important. And what it is his explanation as he begins to explain a concept that we all take for granted that is not true. Like, you ever hear some of those things where they say, this is something that everybody believes, but it's just not true? He's about to show us one of those. And it took me a while to even wrap my head around that concept. So I'll just play it here, and if you have any thoughts, go ahead and put them in the chat.
Unlike a battery, the electricity in the grid comes in the form of alternating current, or AC, which means electrons in the power lines are just wiggling back and forth. They never actually go anywhere. So if the charges don't come from the power plant to your home, how does the electrical energy actually reach you? When I used to teach this subject, I would say that power lines are like this flexible plastic tubing, and the electrons inside are like this chain. So what a power station does is it pushes and pulls the electrons back and forth 60 times a second. Now at your house, you can plug in a device like a toaster, which essentially means allowing the electrons to run through it. So when
Let's cover that basic thing. So he's talking about the difference between alternating current AC and direct current DC. Now, some of the things that I remember from whatever I learned way back when is that when Thomas Edison was starting to do his experiments with creating a light bulb, he found out pretty quickly that you want to, or rather, alternating current is a much better form of creating or transmitting electricity than direct current. And there's many different reasons for that, but let's just go with the basics now that 99% of everything that comes into the common household is alternating current, from everything that powers the cities, everything that powers almost everything is alternating current because they decided that was better than direct current. So if you have any type of electrical device in your house that just plugs straight into the wall and it's got nothing attached, it's just the cord and the plug, that is a device that operates off of alternating current. If you've ever seen the electronic devices that you have, like so many gaming consoles, so many big electronic devices like TVs and things like that, that has a box attached to it. You remember seeing the plugs that look like little black boxes? That is a converter. And that converts the alternating current that comes into the house to direct current for whatever the device is, because that specific device needs direct current. So that part I did learn. The difference between AC and DC. And apparently they've been going with AC for all these years because it's much better than DC for actually transmitting the power. So now he's made this experiment, or this visual device here, where the plastic tube is the power line, the chain inside is the actual electron flow, and now he's just using this wheel on the little thing there to say, you know, this is something that you've attached to the power line like a toaster. And the reason he was pulling the chain back and forth is because with alternating current, the electrons just wiggle back and forth. They flow in one direction, then they switch and they flow back the other direction, and then they keep on switching. And if you've ever heard of hertz, like 60 hertz, 60 Hz, that is, the electrons are wiggling back and forth 60 times in a second. So there's something to deal with all of that part of the process, but at least I know I've got the basics on that. The difference between alternating current, where the electrons wiggle back and forth, and direct current, where the electrons all flow in one direction. Now, he's about to blow that theory completely out of the water and say that no, this concept that we've had all along of the way electricity is, where it's electrons flowing through a wire to a source, that would be direct current, or alternating current, electrons wiggling back and forth in the wire, is completely and utterly patently false. And that we've been believing this concept of how electricity works wrong for the entire time. Somehow we got it in our heads, or maybe we were told in school or whatever, that direct current, electricity, all the electrons flowing down a conductive material like copper wire and into a source or into a receptacle, such as a piece of electronics or something in your house that uses electricity, and then drawing some of that electricity off to use for whatever it is doing, and allowing the rest of it to pass through the completed circuit back towards the source, is completely false. And I never understood, or I've never heard any of this. So this came as quite a shock to me and really piqued my attention when I started listening to this video. So let's continue.
When the power station pushes and pulls the electrons, well, they encounter resistance in the toaster element, and they dissipate their energy as heat, and so you can toast your bread. Now, this is a great story. I think it's easy to visualize, and I think my students understood it. The only problem is, it's wrong. For one thing, there is no continuous conducting wire that runs all the way from a power station to your house. No, there are physical gaps, there are breaks in the line, like in transformers, where one coil of wire is wrapped on one side, a different coil of wire is wrapped on the other side, so electrons cannot possibly flow from one to the other. Plus, I mean, if it's the electrons that are carrying the energy from the power station to your device, then when those same electrons flow back to the power station, why are they not also carrying energy back from your house to the power station? I mean, if the flow of current is two ways, then why does energy only flow in one direction? These are the lies you were taught about electricity. That electrons themselves have potential energy, that they are pushed or pulled through a continuous conducting loop, and that they dissipate their energy in the device.
Yeah.
My claim in this video is that all of that is false. So how does it actually work?
I mean, you know, that just kind of throws out completely everything that most common people understood about electronics forever. I mean, even when I was a kid and I had one of those little science electronic experiment kits, you know, with the little springs on it, and you attach the wires and you make a circuit according to what they say, and you produce something like, you know, lighting up an LED, or creating a tone, or, you know, some other thing that they, you know, 30-in-1 science electronic experiments. That was the whole concept that I thought I understood, is that electricity was the flow of electrons going in a specific direction and delivering their energy to the device that was connected to the circuit. And that apparently is completely wrong.
And 70s, there was a huge breakthrough in our understanding of the universe when Scottish physicist James Clerk Maxwell realized that light is made up of oscillating electric and magnetic fields. The fields are oscillating perpendicular to each other, and they are in phase, meaning when one is at its maximum, so is the other wave. Now, he works out the equations that govern the behavior of electric and magnetic fields, and hence these waves. Those are now called Maxwell's equations. But in 1883, one of Maxwell's former students, John Henry Poynting, is thinking about conservation of energy. Now, if energy is conserved locally in every tiny bit of space, well, then you should be able to trace the path that energy flows from one place to another. So think about the energy that comes to us from the sun. I mean, during those 8 minutes when the light is traveling, the energy is stored and being transmitted in the electric and magnetic fields of the light. Now, Poynting works out an equation to describe energy flux. That is, how much electromagnetic energy is passing through an area per second. This is known as the Poynting vector, and it's given the symbol S. And the formula is really pretty simple. It's just a constant, 1 over mu naught, which is the permeability of free space, times E cross B. Now, E cross B is the cross product of the electric and magnetic fields. Now, the cross product is just a particular way of multiplying two vectors together, where you multiply their perpendicular magnitudes, and to find the direction, you put your fingers in the direction of the first vector, which in this case is the electric field, and curl them in the direction of the second vector,
see,
the
all of
magnetic
this
field,
is
then your
just
thumb
complete and utter
points in the
Greek to
direction
me.
of the resulting vector, the
He's
energy
talking
flux.
about all the
So what
the
this shows us
science,
about
math, mumbo
light
jumbo that
is that
you
the
apparently
energy
have
is
to
flowing
have
perpendicular to both the electric and the
very
magnetic
specific
fields.
understanding
And
of
it's in the same
electromagnetic
direction
energy
as the
in
light
order
is
to
traveling.
understand what the
So
hell
this
he's
makes a
talking
lot of
about.
sense. Light carries energy from its source out to its destination. But the kicker is this. Poynting's equation doesn't just work for light. It works anytime there are electric and magnetic fields coinciding. Anytime you have electric and magnetic fields together, there is a flow of energy, and you can calculate it using Poynting's vector.
To illustrate this, let's consider a simple circuit with a battery and a light bulb. The battery by itself has an electric field, but since no charges are moving, there is no magnetic field, so the battery doesn't lose energy. When the battery is connected into the circuit, its electric field extends through the circuit at the speed of light. This electric field pushes electrons around so they accumulate on some of the surfaces of the conductors, making them negatively charged, and are depleted elsewhere, leaving their surfaces positively charged. These surface charges create a small electric field inside the wires, causing electrons to drift preferentially in one direction. Note that this drift velocity is extremely slow, around 1/10 of a millimeter per second. But this is current. Well, conventional current is defined to flow opposite the motion of electrons, but this is what's making it happen. The charge on the surfaces of the conductors also creates an electric field outside the wires, and the current inside the wires creates a magnetic field outside the wires. So now there is a combination of electric and magnetic fields in the space around this circuit. So according to Poynting's theory, energy should be flowing. And we can work out the direction of this energy flow using the right-hand rule. Around the battery, for example, the electric field is down and the magnetic field is into the screen. So you find the energy flux is to the right, away from the battery. In fact, all around the battery, you'll find the energy is radially outwards. Energy is going out through the sides of the battery into the fields. Along the wires, again, you can use the right-hand rule to find the energy is flowing to the right. This is true for the fields along the top wire and the bottom wire. But at the filament, the Poynting vector is directed in toward the light bulb. So the light bulb is getting energy from the field. If you do the cross product, you find the energy is coming in from all around the bulb. It takes many paths from the battery to the bulb, but in all cases, the energy is transmitted by the electric and magnetic fields.
People seem to think that you're pumping electrons and that you're like buying electrons or something, which is just so wrong. For most people, and I think to this day, it's quite counterintuitive to think that the energy is flowing through the space around the conductor. But the energy which is traveling through the field, is going quite fast.
If you work in IT, you need Terra.
All right.
An all-in-one remote monitoring and management solution to run your...
So
that
portion of it, what he's basically saying is that electrons are flowing, but at an extremely small rate, and that is what we call current. But it's so slow, about, I think he said 1/10 of a millimeter a second, that is not possibly where the energy could come from. So instead, what the energy is coming from is the electronic and magnetic fields that are created when you have the complete circuit. And those fields create the conditions in which you will get waves of that electronic and magnetic energy moving in tandem towards whatever source. And I still can't wrap my head around what he's talking about with this stupid right hand rule, and how you determine how that energy flows. But at least I got that part of it, and I got to thinking about it, and I said, okay, let's try to find something a little more practical to describe and understand that. And what I came up with is the way water moves in waves on, say, the lake or the ocean. So over time, wind pushes small amounts of water in a very specific direction. And the more pressure there is, the more a wave is going to be created. So you look at a wave of water that's moving along a specific path from out in the ocean towards the beach, and you would say, okay, all that water there is moving towards me. But that's not quite right, because if you watch things like boats or buoys or even birds that are sitting on the water, the actual position of those items is not affected that much. It stays in the relatively same area. A boat that is hit by, say, a 1 foot wave rises up to the top of the wave with the level of the water and then goes right back down. But it doesn't actually really get closer to the shore, and maybe doesn't even go any further out towards sea. It kind of stays where it is and just goes up and down. So the concept from that I think I understand is that the small amount of water that constitutes a wave doesn't actually move towards the shore. It stays where it is and just moves up and down, just like the boat. Or maybe even a better way to describe that is to consider the in a sporting arena, when you have a whole bunch of people that are engaging in that thing called the wave, where as it approaches you, as soon as it hits you, you stand up and raise your arms up and then sit right back down as soon as the wave has passed. And if you do it in the right timing, it looks like a wave is going through the crowd. But none of the people are actually moving in the direction of the wave. They're just going up and down where they are. So I think what I garnered from that is that the electrons are not actually moving except for a little bit where they are. What is moving is the wave of the electromagnetic energy itself. And therefore it's pushing the power of that wave along with it in the direction it's flowing, but it's not taking any electrons with it. They're just moving up and down as the waves pass over their position. And yet you can still feel the power of a wave as it moves along its path and then hits the shore and ends. And yes, some water is moved in that part of it because of physics, and where else are they going to go but up onto the shore, but then they go right back down into the water because of gravity, only to be picked up again with the next wave and moved onto the shore. And that's a measurable force. We have in existence now electricity producing devices that rely on wave technology. So they'll put like an air filled pontoon or just a something like that on the surface of the water, and when the wave comes it raises it up, and then it goes back down once the wave passes, and then that is attached to something that takes that force, that energy, that is causing the up and down movement and translating it into, like, a turbine that produces electricity. And more than likely what we're talking about is that the production of, or rather, the use of electricity is actually translating the power that is being transmitted with those waves into something that we can utilize. And it's not actually stealing electrons or borrowing electrons or anything like that to then dissipate into heat. It's the energy that is being carried by the wave of electromagnetic energy that is then taken from that and then used to produce whatever result, lighting the light bulb, running the microwave. And eventually, if you're running off of a battery source, you will deplete the energy that it can provide, because you're stealing the energy from the waves, not the electrons. All the material, all the atomic material is still there. Protons, neutrons, electrons, all that's still there, but you have taken the energy that is available from that and depletes it. So I think in that regard, I've got the basic concept of that. Just as you would understand that there's no actual, you're not stealing water from the sea continually. It's creating, it's almost like it's using the water, or in this case, the electrons, as the medium for transmitting the force. So I got to imagine there's some kind of relation to physics there, because you can definitely transmit force without transmitting energy. I'll have to think on that more and see if there's something further I can come up with. But in any case, let's continue on with this and see if there's any more insights we can garner.
There are a few things to notice here. Even though the electrons go two ways, away from the battery and towards it, by using the pointing vector, you find that the energy flux only goes one way, from the battery to the bulb. This also shows it's the fields and not the electrons that carry the energy.
I mean, how far do the electrons go in this little thing you're talking about? They barely move. They probably don't move at all.
Now, what happens if in place of a battery we use an alternating current source? Well, then the direction of current reverses every half cycle. But this means that both the electric and magnetic fields flip at the same time. So at any instant, the pointing vector still points in the same direction, from the source to the bulb. So the exact same analysis we used for DC still works for AC. And this explains how energy is able to flow from power plants to homes in power lines. Inside the wires, electrons just oscillate back and forth. Their motion is greatly exaggerated here, but they do not carry the energy. Outside the wires, oscillating electric and magnetic fields travel from the power station to your home. You can use the pointing vector to check that the energy flux is going in one direction. You might think this is just an academic discussion, that you could see the energy as transmitted either by fields or by the current in the wire. But that is not the case. And people learned this the hard way when they started laying undersea telegraph cables. The first transatlantic cable was laid in 1858.
It only worked for about a month. It never worked properly.
There are all kinds of distortions when they try to send.
Enormous amounts of distortion. I mean, they could work it at a few words per minute.
What they found was sending signals over such a long distance under the sea, the pulses became distorted and lengthened. It was hard to differentiate dots from dashes. To account for the failure, there was a debate among scientists. William Thomson, the future Lord Kelvin, thought electrical signals moved through submarine cables like water flowing through a rubber tube. But others, like Heaviside and Fitzgerald, argued it was the fields around the wires that carried the energy and information. And ultimately, this view proved correct. To insulate and protect the submarine cable, The central copper conductor had been coated in an insulator and then encased in an iron sheath. The iron was only meant to strengthen the cable, but as a good conductor, it interfered with the propagation of electromagnetic fields because it increased the capacitance of the line. This is why today most power lines are suspended high up. Even the damp earth acts as a conductor.
Okay, I want to stop there because I had thought to myself many years ago. Here, let me switch over to this for a second here. So, where are we here? There we are. I had thought to myself many years ago that it seemed to me to be a stupid thing to take something like power transmission and put it on a stick 30 feet above the ground where it is highly susceptible to wind and rain and tornadoes and ice and whatever else, the weather that we have in all the various parts of the country that could easily damage those things. Why in the world would we take the lines that we are transmitting electricity from power generation to the people that need it and putting it way up in the air where it is susceptible to being damaged by weather? And I didn't understand that thing, and I saw this, and okay, so that makes sense. What he's basically saying there is that the ground itself is interfering as a conductive element because of the minerals or the water or whatever else is in the ground. That's why when lightning strikes, it goes to ground, always. It's attempting to get to ground. And that is a discharge of electricity from what is being created in the air down to a conductive element. Conductive meaning it will receive and not resist the flow of electricity down to the ground. So lightning always is trying to get to ground. And it makes sense to me now that what he's saying is because of the conductivity of the ground, if you put electrical wires, transmission lines, in the ground or even close to the ground, it's going to interfere with the signal. In other words, they put power lines way up in the fucking air to improve the quality of the electricity being transmitted, so it doesn't get the interference from the ground. And more recently, I've seen some housing developments where they don't have power lines up in the air. All of the electrical lines to newer housing developments are buried in the ground. And I did a little bit of research on that, and I found out that the reason they, or what they're doing to compensate for the conductivity of the ground, is that they put very heavy shielding on those wires, non-conductive shielding on those wires so that the conductivity of the ground does not interfere with the power transmission. However, to do that, the materials required to have that heavy of shielding on those wires so that the conductivity of the ground will not interfere with the power transmission is very expensive. And they actually roll it into the price of new homes. So if you go out to, say, the country or some area that just hasn't been developed yet, and all of a sudden you see a housing development where they're cropping up, 20, 30, 40 houses and building a whole new street. If they are not connecting that, they're actually taking all of that, the expensive cost of running those electrical wires under the ground so that there is no transmission lines up high anymore, and adding that to the cost along with the road and the sewers. All of that is rolled into the cost of the house, all the houses that are there. So if you're in a new housing development, you're paying so much more money for the potential amenities that come along with that housing development. You're paying an extra charge for electricity transmission lines being buried in the ground, except on, as opposed to being on poles up in the air. And you're paying for brand new sewer work, and you're paying for the road that runs between the houses. And all that's rolled into the price of these new houses. And then you look at new houses that are being built, all of them, all of the new houses that are being built start at $250,000. There are no $100,000 brand new homes anymore. Okay, and the reason why is because of the way they're doing these developments. I found all of this out, and I'm like, holy fucking shit. Okay, so at least that answers that portion of it. Is that because you cannot necessarily, I mean, you can now with the technology, insulate a wire well enough so that the ground does not interfere with the transmission of electricity, and it is possible to bury the transmission wires. But up until more recently, I think they started that maybe in the late 90s, and up until then, it was up above, on poles. And even still, let's say you have housing and urban development buildings, or housing, HUD housing, or you have apartment complexes that are designed for low-income people. I can almost guarantee you that those are going to have standard power lines strung up on poles and then into the buildings, because it's cheaper. It's cheaper to produce and cheaper to create, to build and put together, and all of that. And they know they're not going to get as much money as, say, a housing development where every single house is a minimum of $250,000 times 40 houses. Okay, and we're talking now about $10 million for a single housing development. Not to mention, what else is going on with that, the property values and all that stuff. So I found that rather interesting, that the process by which we are determining how infrastructure is built is based on not only how much it costs, but how relevant it is to what they want to accomplish. So if you want a nice house, you're definitely paying for it, and you're probably paying more than it's actually worth for them to be able to do that. All right, let's get back to this for the last part of the video.
So you want a large insulating gap of air to separate the wires from the ground.
So what is the answer to our giant circuit light bulb question? Well, after I close the switch, the light bulb will turn on almost instantaneously in roughly 1/c seconds. So the correct answer is D. I think a lot of people imagine that the electric field needs to travel from the battery all the way down the wire, which is a light second long, so it should take a second for the bulb to light up. But what we've learned in this video is it's not really what's happening in the wires that matters. It's what happens around the wires. And the electric and magnetic fields can propagate out through space to this light bulb, which is only 1 meter away, in a few nanoseconds. And so that is the limiting factor for the light bulb turning on. Now, the bulb won't receive the entire voltage of the battery immediately. It'll be some fraction, which depends on the impedance of these lines and the impedance of the bulb. Now, I asked several experts about this question and got kind of different answers, but we all agreed on these main points. So I'm going to put their analysis in the description in case you want to learn more about this particular setup.
If I get called out on it and people don't think it's real, we can definitely invest the resources and string up some lines and make our own power lines in the desert.
I think you're going to get called out on it.
I agree. I think you're going to get called out.
So I think that's right.
I think it's just kind of wild that this is one of those things that we use every day that almost nobody thinks about or knows the right answer to.
Agreed.
These traveling electromagnetic waves around power lines are really what's delivering your power. Hey, now that you understand how electrical energy actually flows, you can think about that every time you flick on a light switch. And if you want to take your switches to the next level, the sponsor of this video...
Okay, that's enough of that. All right, so obviously that is a concept that, as he said, most people don't understand, most people don't think about. If what he is saying there is true, then we have thought wrong about how electricity flows for as long as humanity has known about electricity. And as far as what that means for what I'm doing, I'm going to be trying to increase my knowledge on electrical theory. And that means I do have to start from the beginning. And so some of that I may be streaming on this series, some of it I may not. That's just something that I know I'm going to want to increase my own knowledge as time goes on. And it's probably going to be something that is either a never-ending journey, and I just spend a little bit of time going at it here and there over God knows how long, or maybe it's something that I can get relatively quickly, because I mean, we do have people in our world that understand electricity very well. Obviously, this is not a big deal for some people, but they've also probably gone to college and are masters and doctorates in whatever this is, and that certainly isn't the route that I'm going to be able to take or want to take with this. But I think there's enough that exists in free things that are available on the internet that I can gather enough information to do what I think I want to do with this, which is essentially being able to repair electronics by myself, to be able to pull out a piece of electronic and say, okay, let's find out what's wrong with this, test it and determine what's wrong, and then fix it. So, Joel brings me one of his broken Nintendo consoles, and it may take me a while, but I can diagnose it and then fix it, and then we have a working Nintendo console. Now, there's quite a few people out there that do this sort of thing. And one of the things I've been fascinated by over the years is videos that they have on YouTube of people that restore things, particularly electronics. And I've watched some of how this is done, and I think to myself, oh, hey, I'd love to do that, maybe I could do that. If I'm going to do it right, I definitely have to have this aspect of it where I understand at least the basic underlying principles of electricity and how it all works, the components, the setup. Years ago, probably because I had one of those stupid little kits with the springs, I did have a basic understanding of it, but that was also 20 plus years ago, and I've forgotten most of it. So I do need to get back into that. Again, that may be some of that on stream here on the WreckTech series. Others, it may be just on my own time. I don't know what I want to present. So at the very least for this stream, I wanted to give you an idea of how this all works. And that's why I bought this kit where I got all these brand new pieces. Because in order to test a piece to see if it is still working, a component of a circuit board, it cannot be in the circuit board. Other things in the circuit board are going to change the things that you need to know about that. So you literally need to take the component out of the circuit board in order to test it to see if it is good. And then if it is not good, I've got the pieces here to be able to replace it in that circuit board. And then know that what I'm putting into the circuit board is good, and therefore the circuit and the way it's designed to work is good, and that part of it is supposed to be good. There's much more dealing with some portion of it that has to deal with the software, the programming, and all that other stuff that I may never get into, but at least this portion of it, the hardware, I think I can do this. I'm pretty damn sure I can do this, and I just need to increase my knowledge on it a little bit more and have a little bit better understanding. So that's the direction I'm going with it. I didn't set up anything else with upcoming events here like I normally do, so let me just double check here and let's see what's coming up, because I know a lot of shit is coming up right now. In fact, let me do something here. Give me 1 second. Oh, well, while we're waiting, let's get some music back here. All right. Let me see here. No, I don't have any of that ready. Okay, so let's just do it this way. Here is what you need to know is coming up. Wednesday night. You know, actually tomorrow I'm probably gonna... You can't crouch down and hunch your back, Joel, and act like people can't see on the fucking camera.
I was stopping myself from falling.
Uh-huh, sure. You were like Quasimodo back there. He can't see me. So tomorrow night, at least until I've got a new series that is going to be premiering on, I think, September 6th. And that's going to be our every Tuesday night series. But until then, I'm going to just do some no-cam streams from my house on Tuesdays. So I think I'll start that tomorrow. And that also is going to be a chill stream. We'll just have some music going, and I'm going to be cleaning up my music collection because it is a complete and utter disaster. I DJ'd from 2001 until 2016. And I have not touched my music collection since then. And I'm talking about the digital version. All the discs are packed away in the file cabinet, and I probably won't touch them. But the actual digital collection is a complete mess. So all that would be, if you are interested in joining me, is cleaning up the collection, making sure things are properly named and in their proper place, and it's you know, probably just as boring as this is. So we'll probably be doing those on Tuesday. Wednesday, this coming Wednesday, July 27th, I'm going to be showing The Green Mile with Tom Hanks in the Conflux. The next day, Thursday the 28th, That's Not Real Trek continues. We're watching Discovery Season 1, Episode 11 and Episode 12 with Short and Sweet. Short and Sweet is showing cartoons again this Saturday morning, 10 a.m. in the Conflux. Then Saturday night, Cage and V doing their Saturday night double feature. They're showing All Hallows Eve from 2013 and Terrifier, which it was like a spin-off from All Hallows Eve, showing the same bad guy, a sadistic murderer known as Art the Clown from 2016. So if you're into the horrors and all the scary stuffs, that's Saturday night at 10 p.m. in the Conflux. Then this is important. Hold on a second. This I gotta put the thing in the thing with the thing on. Hold on. Let's get this right here. Okay. It's kind of small, but Whitney's 10-hour comeback horror extravaganza. Sunday, July 31st, starting at noon and going all the way until 10 p.m. On her channel, she is rebranding, and you definitely want to check it out. That's, which Whitney? Here, I'll put it in the thing now, just in case anybody is here and they don't know. Let me see if I can do this right. There we go. 10 hours of horror from the queen of Scream and horror herself. Check that out. And then I'll just scroll down here a week later. Sunday, August 7th, the Gaming Avengers are doing their 2-year anniversary. And for that, they're doing 12 hours as a charity stream to benefit the organization To Write Love on Her Arms. And that starts at 10 a.m. Central Time, so that's 9 a.m. Eastern or 8 a.m. Pacific, and it goes for 12 hours. And then finally, our next audio drama, Calm Violence, is going to be the following Sunday after that. So Sunday, July 31st is Whitney's big stream. Sunday, August 7th is the Gaming Avengers big stream, and then Sunday, August 14th is the 5th audio drama from EBC, Calm Violence, and that stars Iznib and Tubaswan and Malaysia. And we have a special time for that. That will be 3 p.m. Eastern, right here on EBC 2021. Okay, so that's about it. Enough of that. I don't need to do anything else here. Let's find somebody to raid, and then I will catch you all later. The few people who have been maintaining themselves here, I thank you. Like I said, it was going to be a boring stream. Oh, let me do this real quick for anybody that needed the link for that. Alright, let's find somebody to raid. Let's see, we've got Soldrake. Let's go do the people themselves, the Gaming Avengers. They are streaming now some Kingdom Hearts. And remember, their big stream is a week from Sunday on August 7th. All right, there we go. Thank you very much for joining me. I will see you, I guess, tomorrow night if I have everything set up for another chill stream where I'm just going to be renaming files, basically, and playing music. So I'm probably going to do that in Discord. Yeah, in fact, I know for certainty I'll be doing that in the Discord. It's not on the schedule, but I'll be putting that on there soon, and you can check that out if you're interested. And otherwise, I'll just take some requests and play some music and just work away in the background. And then Wednesday for the Green Mile in the Conflux. We'll see you there for that. Don't do anything I wouldn't do because, well, yeah, you probably figured out by now. I'm not going to do that shit, okay? Thank you. Adios. Goodbye. See ya.